Imagine descending into darkness, not the darkness of night on Earth, but the absolute, ancient darkness of Mars. A cavern untouched by sunlight for billions of years. Your suit lights carve thin beams through air so thin it barely exists, illuminating walls of volcanic rock that curve away into shadow. Above you, hundreds of feet of stone and regolith stand between you and the radiation-soaked surface. The deadly cold, the unbreathable atmosphere, the cosmic rays that slice through everything exposed beneath that salmon-pink sky. Down here, you think, we are finally safe. This is the dream that has captured imaginations across the world. The underground Mars colony. Humanity sheltered beneath the red planet's crust, protected from radiation, insulated from temperature extremes, hidden away in lava tubes and excavated chambers where life can finally take root. It is elegant. It is logical. It has become the cornerstone of nearly every serious Mars colonization proposal. Dig down. Build deep. Let the planet itself become our shield. But what if I told you that even there, buried beneath layers of Martian stone, danger follows you in ways that most people never consider? What if the very ground meant to protect you carries threats that no amount of rock can filter away? What if the engineering challenges of living underground on Mars are not just difficult, but exist at the very edge of what human technology and biology can endure? Tonight, we will descend together, not into a Martian cave, but into the hidden complexities that make underground habitation far more perilous than it first appears. We will journey through Martian geology, where the ground beneath your feet is not solid sanctuary, but a fractured, unstable archive of ancient violence. We will trace invisible radiation as it penetrates rock itself, transformed but not stopped, creating secondary particles that fill your shelter with unseen hazards. We will examine the soil, beautiful red dust that coats everything, laced with perchlorates so reactive they poison both machinery and flesh. We will explore what happens to the human body when confined in artificial darkness, breathing recycled air, drinking reclaimed water, living in a closed loop where every failure cascades into crisis. We will look honestly at engineering problems that have no Earth equivalent, construction in near vacuum, life support systems with no margin for error, and the haunting reality that underground escape becomes exponentially harder. And we will ask the deeper questions. Not just can we survive beneath Mars, but what would that survival cost? What would it do to us? And why, despite everything, do we still dream of it? This video is designed for those quiet hours, for contemplation before sleep or during moments when the mind wanders toward distant horizons. The pace will be gentle, the tone reflective. There is no urgency here, only curiosity and the patient unfolding of ideas that deserve more than headlines. If this kind of journey appeals to you, if you find wonder in the spaces between hope and reality, please consider liking this video and subscribing. It helps us continue exploring these questions together, diving deeper into the science and philosophy of worlds beyond our own. And I would love to know, where are you right now? What part of the world are you watching from? And what time is it in your corner of Earth? Leave a comment below. There is something quietly profound about knowing that while we explore Mars together, you might be watching at dawn in Tokyo, at midnight in Berlin, or during a quiet afternoon in Sao Paulo. Wherever you are welcome here. Now, settle in. Let your thoughts drift downward with us, past the surface of Mars, past the radiation and the cold, into the depths where humanity hopes to build its first extraterrestrial home. Let us see what waits in the darkness. Let us begin. Mars greets visitors with silence. Not the peaceful quiet of a forest at dawn, but the absolute, crushing silence of a world without air to carry sound. The surface is a study in hostility, a landscape sculpted by forces that have no regard for biological life. To stand unprotected on the Martian surface is to experience conditions so extreme they defy our earthly intuition about what a planet should be. The atmosphere, what little exists, is less than 1% the density of Earth's. It is so thin that liquid water cannot exist on the surface. Any exposed moisture would instantly boil away, even in the freezing cold. And it is cold, devastatingly so. Temperatures average around -80 degrees Fahrenheit, but at night, particularly near the poles, they plunge to -200 degrees. Metal becomes brittle. Rubber shatters like glass. The human body, accustomed to the thermal stability of Earth, would freeze in minutes without protection, cells rupturing as water within them crystallizes into jagged ice. Then there are the dust storms, not the romantic whirlwinds of science fiction films, but planetary phenomena that can engulf entire hemispheres for months at a time. Martian dust is extraordinarily fine, closer to smoke than sand, and it carries a static charge that causes it to cling to everything. Solar panels become obscured. Machinery ceases. The sky transforms from its usual butterscotch hue to an impenetrable rust-colored darkness. During these storms, the already faint sunlight dims to twilight levels, and temperatures drop even further. The dust itself is laced with perchlorates and other oxidizing compounds, making it not just an annoyance, but a chemical hazard. But perhaps the most insidious threat on Mars's surface is invisible. Without a substantial atmosphere, and without a protective magnetic field like Earth's, Mars is exposed to the full fury of cosmic radiation. This is not the benign sunlight that warms our planet. This is high-energy particles streaming in from distant supernovae, solar flares unleashing torrents of charged particles, and galactic cosmic rays that can penetrate deep into matter. On Earth, our atmosphere and magnetosphere shield us from most of this radiation. We live beneath an invisible umbrella that has protected life for billions of years. Mars has no such protection. The magnetosphere that once existed died billions of years ago when the planet's core cooled and solidified. Now, radiation pours onto the surface unimpeded. A single solar particle event, a burst of radiation from the sun during a solar storm, could deliver a lethal dose to an unshielded astronaut in hours. Even the continuous background radiation, the steady drizzle of cosmic rays, accumulates to dangerous levels. Estimates suggest that astronauts on the Martian surface would receive radiation doses equivalent to a full-body CT scan every few days. Over months and years, this would drastically increase cancer risk, damage the central nervous system, and accelerate cellular aging. The surface of Mars, despite its dusty beauty and ancient river valleys, is fundamentally incompatible with human biology. Faced with these realities, scientists and engineers began asking a logical question. If the surface is uninhabitable, what about beneath it? The idea of underground habitation on Mars is not born from cowardice or lack of imagination. It emerges from careful analysis of the challenges and a search for practical solutions. Underground, many of the surface problems diminish or disappear entirely. Temperature variations stabilize. Radiation is attenuated by layers of rock and soil. Dust storms become irrelevant. The ground itself becomes a shield, offering protection that the thin atmosphere cannot provide. This thinking has deep roots in the scientific literature. NASA has explored concepts for underground habitats for decades. Early Mars mission architectures in the 1990s proposed inflatable habitats covered with Martian regolith for radiation shielding. By the 2000s, attention shifted to natural features, particularly lava tubes, vast underground caverns formed by ancient volcanic activity. Mars, once geologically active, is dotted with evidence of volcanism. Olympus Mons, the largest volcano in the solar system, towers over the landscape, and around such features, researchers have identified what appear to be collapsed sections of lava tubes, skylights that hint at vast networks beneath the surface. Studies from institutions like Purdue University and the European Space Agency have mapped these potential underground structures using orbital imagery and ground-penetrating radar. Some lava tubes on Mars may be enormous, hundreds of feet in diameter and miles long, large enough to house entire settlements. Within these natural shelters, colonists could theoretically build pressurized habitats protected from radiation, insulated from temperature extremes, and shielded from the abrasive dust. The logic is compelling. Nature has already done much of the excavation work. Why not use it? SpaceX, in its ambitious plans to establish a self-sustaining city on Mars, has acknowledged the necessity of radiation protection. While specific architectural details remain speculative, Elon Musk and other company representatives have discussed the potential for underground or heavily shielded habitats. Academic papers have proliferated, proposing everything from 3D printed habitats using Martian regolith mixed with polymers to robotic excavation of subsurface chambers sealed with airtight membranes. The consensus across much of the scientific community is clear. If humans are to survive on Mars for extended periods, they cannot remain on the surface. They must go down. This is not foolish thinking. It is the product of rigorous analysis by some of the brightest minds in planetary science and aerospace engineering. The underground solution addresses the most immediate and lethal threats that Mars presents. It is pragmatic, grounded in the physics of radiation shielding and thermal dynamics. In many ways, it represents the best hope for making Mars habitable within the constraints of current or near-future technology. But as we prepare to descend beneath the Martian surface, a question begins to emerge, quiet at first, then growing more insistent. What exactly are we escaping by going underground? We avoid the radiation, certainly. We shield ourselves from the cold and the storms. But do we truly escape the fundamental challenges of Mars? Or do we simply trade one set of problems for another, perhaps more subtle, perhaps more profound? The underground habitat promises safety, yet safety is not the same as survival. Shielding is not the same as thriving. As we examine the Martian geology, the chemical composition of the soil, the closed systems required for life support, and the psychological toll of existence beneath the surface, we begin to see that the answer to Mars's hostility may not be as straightforward as burrowing into its crust. The ground beneath our feet on Mars is not merely rock and dust. It is a frontier of challenges we are only beginning to understand. And the deeper we go, the more complex those challenges become. Before we descend into the Martian underground, we must first understand what lies beneath. The ground is not just a foundation. It is a history book written in stone, a record of ancient volcanoes, vanished rivers, and atmospheric transformations spanning billions of years. To build a shelter beneath the surface of Mars is to trust geology we have never touched, rock formations we have only glimpsed from above, and cave systems we have theorized but never entered. The Martian subsurface is not simply dirt and stone. It is a frontier of profound uncertainty. Our knowledge of what lies beneath Mars comes from a careful assembly of distant observations. Orbital cameras peer down from above, mapping the topography with extraordinary precision. Ground-penetrating radar aboard spacecraft, like Mars Reconnaissance Orbiter, sends electromagnetic pulses into the crust, revealing hidden layers of ice, buried impact craters, and the shadowy outlines of subsurface structures. Rovers on the surface drill shallow holes, scraping samples from the regolith, the loose blanket of dust and broken rock that covers much of the planet. And in 2018, the InSight lander deployed a seismometer, listening for the faint tremors of Marsquakes, allowing scientists to construct the first crude map of Mars' interior structure. What these instruments reveal is a world vastly different from Earth. The Martian regolith is not soil in the way we understand it. There is no organic matter, no microbes churning through decay, no roots binding particles together. Instead, it is a fine, powdery mixture dominated by iron oxides that give Mars its characteristic rust-red hue. Sulfates formed from ancient volcanic eruptions and water interactions, and perchlorates, highly reactive salts that permeate the dust. These perchlorates are not just present in trace amounts. They make up several % of the regolith in many locations, a concentration high enough to pose serious chemical hazards to any habitat or human body that encounters them. Beneath the regolith lies bedrock, layers of basaltic rock formed from ancient lava flows that once covered vast stretches of the planet. Mars was volcanically active for billions of years, its interior churning with heat, spewing molten rock across its surface, and carving enormous shield volcanoes like Olympus Mons, the tallest mountain in the solar system. As these lava flows cooled and solidified, they sometimes formed tubes, hollow channels where molten rock once flowed like underground rivers. When the eruptions ceased and the lava drained away, these tubes remained, vast tunnels stretching for miles beneath the surface, theoretically stable, theoretically shielded from radiation, theoretically perfect for human habitation. The discovery of potential lava tubes on Mars has sparked immense excitement. Orbital images show collapsed sections where the roofs of these tubes have caved in, revealing dark pits that descend into shadow. Some of these openings are enormous, wide enough to swallow a football stadium. If the tubes remain intact beyond these collapsed sections, they could provide natural shelters, pre-made caverns requiring no excavation, offering protection from radiation, temperature extremes, and micrometeorite impacts. On Earth, lava tubes in places like Hawaii and Iceland have served as shelters for centuries, their interiors remarkably stable, their temperatures moderated by the insulating rock. But Mars is not Earth, and this is where certainty begins to dissolve. We have never entered a Martian cave. We have never walked through a lava tube on Mars. We have never touched the walls, tested their structural integrity, or measured the subtle vibrations that might indicate instability. Every assumption we make about the safety and suitability of Martian underground environments is based on inference, modeling, and hopeful extrapolation from terrestrial analogues. The geological processes that shaped Mars are fundamentally different from those on Earth. Mars lacks plate tectonics. Its crust is older, more rigid, and has been bombarded by impacts for billions of years without the resurfacing mechanisms that renew Earth's geology. The rock may be more fractured, more brittle, more susceptible to collapse than we imagine. Marsquakes detected by InSight reveal that Mars is not geologically dead, but it is far quieter than Earth. The tremors are subtle, infrequent, and originate from deep within the planet's cooling interior. Yet even small seismic events could destabilize underground structures. A crack propagating through ancient basalt, a section of ceiling weakened by thermal cycling over millions of years, the gradual erosion of support pillars by chemically aggressive groundwater that may have flowed through these tubes eons ago. On Earth, cave-ins are rare in well-studied lava tubes, but they do happen. On Mars, where no human has ever surveyed the integrity of a single tunnel, the risk is unknown. There is also the question of scale and variation. Not all lava tubes are created equal. Some may have thick, robust ceilings capable of supporting vast chambers. Others may have ceilings thinned by erosion or weakened by ancient impacts that sent shockwaves rippling through the crust. The images we see from orbit show only the surface. What lies deeper remains hidden, a geological mystery waiting to be unraveled by the first explorers who dare to descend. And then there are the geological surprises, the unknowns that no model can predict. Mars has experienced a complex history involving water, ice, volcanic activity, and atmospheric changes. Beneath the surface, there may be layers of ice-cemented regolith, pockets of brine trapped in fractures, or regions where ancient hydrothermal systems altered the rock in ways we cannot yet detect. Drilling into these formations without understanding their composition could trigger collapses, release toxic gases, or expose habitats to liquids that would freeze, expand, and crack the very walls meant to protect them. Earth's cave systems have taught us much about subsurface stability, but they also teach us humility. Even on our own planet, caves can be unpredictable. Sinkholes open suddenly, swallowing roads and buildings. Underground rivers carve new passages, destabilizing old ones. Mineral deposits weaken structural supports over time. And these are caves we have studied for centuries, mapped with precision and monitored continuously. On Mars, we have none of this knowledge. We have only hypotheses and hope. The Martian subsurface is not just rock. It is a record of processes we are only beginning to understand, formed under conditions that no longer exist, shaped by forces that have been silent for eons. To trust our lives to this geology is to place faith in assumptions built on incomplete data. It is to believe that the ground beneath our feet will hold, even when we have never tested its strength. As we imagine descending into Martian caves, we must carry with us not just tools and supplies, but an awareness of how little we truly know. The ground beneath our feet is not simply a stage for our survival. It is an active participant in our fate, a geological system with its own history, its own instabilities, and its own indifference to human ambition. The dream of living underground on Mars begins with geology, but geology, as we will see, is only the first of many challenges that await in the Martian depths. You descend into the Martian caves, confident that kilometers of rock above your head will shield you from the radiation that scours the surface. The airlock seals behind you. The red dust settles. In the darkness of your underground habitat, illuminated only by artificial light, you believe you have found sanctuary. But radiation does not respect our intuitions about safety. It does not stop at barriers the way we imagine. Instead, it transforms, adapts, and in some cases, becomes even more insidious as it passes through the very rock we trust to protect us. To understand what awaits you underground, we must first understand what pursues you from above. Space radiation comes in two primary forms, each with its own character, its own rhythm of threat. The first is galactic cosmic rays, or GCRs. These are not rays in the conventional sense, but high-energy particles, primarily protons and atomic nuclei. that have traveled across the galaxy for millions of years. They originate from supernovae, from the explosive deaths of stars far beyond our solar system. By the time they reach Mars, they carry energies so tremendous that they move at nearly the speed of light. They are ancient travelers, cosmic messengers from stellar catastrophes that occurred before Earth's continents took their present shape. The second form is solar energetic particles, or SEPs. These burst forth from the sun during solar flares and coronal mass ejections, sudden violent releases of energy that send waves of charged particles racing through the solar system. Unlike the steady rain of galactic cosmic rays, SEPs arrive in storms. They are unpredictable, sometimes intense enough to deliver a lethal radiation dose in hours to anyone caught unprotected on the Martian surface. While Earth's magnetic field deflects most of these particles away from us, Mars has no such protection. Its magnetic field died billions of years ago when its core cooled, leaving the planet naked to the cosmos. On the surface, these particles strike everything they encounter. They penetrate spacesuits, habitat walls, and human tissue, breaking apart molecules, damaging DNA, increasing cancer risk, and degrading neural function over time. This is why the underground habitat seems so appealing. Rock, after all, is dense. Rock is heavy. Surely enough rock between you and the sky will stop the radiation, will create a haven where human biology can endure. And to some extent, this is true. Rock does attenuate radiation. As cosmic rays pass through matter, they collide with atoms, lose energy, scatter, and eventually stop. Studies suggest that every meter of Martian regolith reduces radiation exposure by approximately 20 to 30%. Descend 10 meters, and the radiation intensity drops considerably. Descend 20 meters, and it drops further still. But here, in the apparent simplicity of depth equals safety, lies a profound and troubling complexity. When high-energy cosmic rays strike rock, they do not simply vanish. They interact with the nuclei of atoms within the stone, silicon, oxygen, iron, elements that comprise the Martian crust. These collisions trigger a process called nuclear spallation, a fragmentation of atomic nuclei that produces secondary radiation. The incoming particle shatters the nucleus it strikes, releasing a cascade of lighter particles, pions, muons, gamma rays, and most significantly, neutrons. This is not merely a transfer of energy, it is a transformation of the threat itself. Neutrons are especially concerning. Unlike charged particles, which can be deflected by electromagnetic fields, or stopped more readily by matter, neutrons have no charge. They are invisible to the forces that govern charged particles. They drift through rock, through metal, through biological tissue with unsettling ease. A neutron can penetrate far deeper into your underground habitat than the original cosmic ray that created it. In some cases, the neutron flux, the density of neutrons moving through the rock, can actually increase at certain depths before it finally begins to diminish. This creates a paradox that defies our intuition. At shallow depths, perhaps 5 to 10 meters underground, you may find yourself exposed to more secondary radiation, particularly neutrons, than you would experience on the surface. The rock above you is not yet thick enough to fully absorb the incoming cosmic rays, but it is thick enough to generate substantial secondary particles. You are, in effect, living inside a radiation converter, where the primary threat has been transformed into something more penetrating, more biologically damaging in certain respects. Research into optimal shielding depths reveals that meaningful protection requires you to go surprisingly deep. Studies conducted by radiation physicists and planetary scientists suggest that to reduce radiation exposure to levels comparable to Earth's background radiation, you would need approximately 15 to 20 meters of solid rock above you. Some estimates push this figure even higher, depending on the composition of the Martian rock and the intensity of solar activity during your stay. Yet even this presents a problem of diminishing returns. As you descend deeper, each additional meter of rock provides less incremental protection than the meter before it. The first 5 meters reduce radiation significantly. The next 5 reduce it somewhat less. The next 5, less still. To achieve truly safe levels where long-term human habitation becomes viable without severe health consequences, you might need to excavate 30, 40, or even 50 meters below the surface. At these depths, you are no longer building a habitat. You are engineering a subterranean city. Consider what this means in practical terms. On Earth, excavating even 10 meters requires enormous machinery, energy, and time. On Mars, where equipment must be transported from Earth or manufactured from limited local resources, where power is scarce and every joule must be carefully allocated, the energy cost of deep excavation becomes staggering. You cannot simply dig with shovels. Martian rock, though weathered by eons of dust storms, is still rock. It must be drilled, blasted, or melted. Each method requires power, lots of it. Drilling through 50 meters of Martian basalt would demand industrial-scale equipment. Boring machines, rock crushers, conveyor systems to remove tailings, ventilation systems to clear dust from the excavation site. All of this infrastructure must be built, maintained, and powered in an environment where generating electricity is already a monumental challenge. Solar panels produce less energy on Mars than on Earth due to the greater distance from the sun and frequent dust storms that coat panels in fine particles. Nuclear reactors could provide consistent power, but they are heavy, complex, and politically controversial to launch from Earth. And then there is the question of time. How long would it take to excavate a habitat deep enough to be safe? Months? Years? During that time, where do the workers live? How much radiation do they absorb while constructing the very shelter meant to protect them? The timeline stretches, the costs multiply, and the dream of underground safety begins to fracture under the weight of physics and engineering reality. But perhaps most unsettling is this. Even at great depth, you are never truly safe. Radiation on Mars is not a problem you solve. It is a condition you manage, a chronic exposure you mitigate but never eliminate. Some fraction of secondary particles will always reach you. The rock above your head becomes both shield and source, protecting you from the sky while simultaneously generating new threats within its atomic structure. In the dim corridors of your underground Martian home, surrounded by stone older than human civilization, you might pause and listen to the silence. No wind reaches you here, no dust storms rattle the walls, but the radiation continues, invisible and patient, streaming through the galaxy, striking the rock, fragmenting into cascades of particles that drift downward toward you through meters of stone, persistent and inescapable. The underground was supposed to be sanctuary. Instead, it is merely a different kind of exposure, a slower burn, a compromise between the harshness above and the impossibility of true safety below. The Martian soil looks quiet, a soft red powder, gently sculpted by wind, resting in endless dunes and plains. It seems harmless, almost inviting. The kind of material you'd imagine piling into sandbags, pressing into bricks, using to bury your habitat beneath a comforting blanket of rock. But in that dust, in those grains you'd shovel, walk on, and breathe around every day, There is a hidden chemistry problem written into the planet itself. Perchlorates. On Earth, they're industrial chemicals, tools of civilization. On Mars, they're part of the landscape. We first discovered them not with a shovel in an astronaut's hand, but with a robotic chemist sitting quietly in the Arctic plains of the Red Planet. In 2008, NASA's Phoenix lander dug into the soil near Mars's North Pole. It melted a small sample of that soil and analysed the salts inside. What came back was unexpected. High levels of perchlorate compounds, far more than what is typically found in natural settings on Earth. Years later, the Curiosity rover in Gale Crater found more evidence. Other missions, orbiters studying the surface from afar, detected signatures that suggested perchlorates might not be an oddity tied to a single region, but part of a global pattern. The more we looked, the clearer it became. This wasn't a local contamination. It was a planetary habit. Perchlorates are molecules built around chlorine and oxygen. On a chemical diagram, they look simple, almost elegant. A central chlorine atom surrounded by 4 oxygens, carrying a strong negative charge. But this simplicity hides a complex behavior. On Earth, we use perchlorates in rocket fuel, fireworks, and explosives. They store oxygen densely, ready to release it in a burst of energy. On Mars, nature has been patient instead of explosive. Ultraviolet light from the sun, unfiltered by a thick atmosphere, batters the surface endlessly. It breaks apart molecules, rearranges them, stitches new ones together. Over millions of years, this radical chemistry has allowed perchlorates to form and accumulate in the dust and regolith. They are not scattered like rare gems. They are woven into the soil like salt in the sea. For human beings, that is a quiet problem with loud consequences. Perchlorates are known to interfere with a small but essential part of human biology, the thyroid gland. This tiny organ in your neck is one of the body's regulators of time, controlling metabolic rate, growth, and development, especially in the brain. To do its job, the thyroid needs iodine. It pulls iodine out of your bloodstream, concentrates it, and uses it to make hormones that tell every cell in your body how fast to live. Perchlorates compete with iodine. They slip into the same transport pathways, blocking the gate. When perchlorate levels are high enough or long-lasting enough, the thyroid can't get the iodine it needs. Hormone levels drop. The body responds, but slowly, imperfectly. On Earth, we've studied the effects in workers, in communities with contaminated water, in carefully measured experiments. The patterns that emerge are subtle but real. Thyroid disruption, fatigue, changes in heart rate and temperature, and in pregnant women and children, possible impacts on brain development and growth. There is also concern, still being studied, that long-term disruption to thyroid function could contribute to cancer risks over time. On Mars, imagine not just a polluted well or river, but the entire environment itself infused with these compounds. The dust you track into an airlock, the regolith you melt for water, the grains caught in filters, seams, and clothing. A world where background exposure is no longer a localized hazard, but simply part of breathing, eating, and building. And this is where the underground dream runs into its next complication. Digging down doesn't escape the perchlorates. They are not painted on the surface like a thin coat of poison. Measurements suggest they are mixed into the regolith, extending at least tens of centimeters below and likely much deeper in many regions. The soil you want for radiation shielding, for bricks, for backfill, carries the same chemical signature. Even if you seal yourself under rock, the dust still follows. Every habitat concept, Every base design must wrestle with the same adversary: infiltration. Martian dust is fine, electrostatically clingy, and restless. It rides in on suits, grinds into joints, floats in the air of pressurized modules. It will settle on floors and filters, on tools and food preparation areas, on every surface that humans touch. On Earth, dust is an inconvenience. On Mars, it is a delivery system. Now orbit that simple fact around daily life. Each time a crew member goes outside, some dust comes in. Each time regolith is processed to extract water, some perchlorate ends up in the system. Every time air is cycled, filters must struggle to keep up. Over months, over years, trace amounts in water, food, and air could accumulate into meaningful exposures. How do we respond? Engineers and scientists have begun to imagine ways to tame this chemical threat. One idea is to wash the soil, flush perchlorates out of regolith with water or brines, collect them, and remove them before the material is used inside. Another approach is heat. Perchlorates can decompose at high temperatures, breaking down into simpler compounds, potentially releasing oxygen as a useful byproduct. There are also biological dreams, specially engineered microbes that could digest perchlorates, turning a toxin into something benign. Each of these is promising in theory, but each carries weight in practice. Washing regolith demands large amounts of water and careful containment, two things that are precious and technically difficult on Mars. Heating soil to decomposition temperatures requires energy, perhaps more than an early base can easily spare. Biological solutions raise questions of containment, reliability, and survival in an alien environment of cold, dryness, and radiation. Even after treatment, perfection is unlikely. Remediation can reduce concentrations, but trace amounts may persist. Filters can capture dust, but not every particle. Habitat designs can include dust locks, air showers, electrostatic cleaning systems, but no barrier is absolute. Managing perchlorates becomes less a single fix and more an ongoing relationship. Continuous monitoring, cleaning, and adaptation. There is another subtler consideration. On Mars, perchlorates do not only threaten us, they also shape how we look for life. These same compounds, especially when combined with UV light, can break down organic molecules, complicating the search for ancient biosignatures in the soil. The chemistry that protects Mars from preserving delicate organics on the surface also challenges our instruments. Underground, shielded from radiation, might be where those fragile clues survive. But the perchlorates likely follow us there too, folded into the very rocks we drill. Researchers on Earth are not ignoring any of this. Laboratories simulate Martian soil, growing plants in perchlorate-rich mixtures to see how roots and leaves respond, and how much of the chemical is pulled into edible tissue. Others study materials and filters designed to block dust more effectively, or model how perchlorates might move through closed ecological systems over time. Some investigate bacteria from Earth's own extreme environments, organisms that naturally transform perchlorates, searching for enzymes or pathways we might one day employ on another world. Still, for now, the Martian soil remains what it is: a global layer of chemically reactive dust, waiting to mix with every plan we make. Living underground protects you from cosmic rays and solar storms. It shelters you from micrometeorites and the violence of the surface environment. But it does not erase the chemistry of the planet. The rocks above might shield you from the sky. The soil beneath and all around carries its own quiet hazard, colorless, odorless, invisible, but persistent. The dream of a Martian cavern city, softly lit and safe, must therefore include not just thick walls and stable ceilings, but complex systems humming in the background. Scrubbers, heaters, filters, reactors, perhaps even living bioreactors, a constant choreography, turning toxic dust into something survivable. In this way, the Perchlorate problem is less a single obstacle and more a reminder. Mars is not trying to kill us, but it is not designed for us either. Every handful of soil we bring inside is a small negotiation with an alien world. Beneath the Martian surface, the world becomes very small. The dust storms fade, the radiation drops, but something else begins to grow, quietly, invisibly. Dependence. On Earth, air and water are background conditions, so constant that they become part of our unconscious. On Mars, underground, they become foreground. Every breath is a transaction with a machine. Every sip of water is an agreement with a system that must never fail. In the dim light of a buried habitat, the universe narrows to a sealed volume of gas and a few thousand liters of liquid circulating through pipes. Outside, the planet is cold, dry, and indifferent. Inside, the atmosphere is young, artificial, and fragile. This is the closed loop. It sounds elegant. A self-contained ecosystem, recycling what it uses, wasting nothing. A tiny Earth under rock and regolith. But the reality is less like a serene terrarium and more like balancing on the tip of a needle, where chemistry, physics, and biology must cooperate without pause. We begin with the air. In an underground habitat, the walls are not porous. There is no breeze. There is no open window. The atmosphere is a fixed mass of gas, constantly reshaped by every breath, every exhale, every chemical process. Humans inhale oxygen and exhale carbon dioxide. On Earth, that CO2 diffuses into an ocean of air and is slowly absorbed by plants, oceans, and soil. Underground on Mars, it accumulates in a room the size of a small building. Left unchecked, it rises silently, odorless and invisible, until the first symptom is not a loud alarm, but a headache, drowsiness, and a strange sense of unease. Managing this is not optional. It is a daily, hourly necessity. CO2, scrubbing becomes the invisible heartbeat of the habitat. Filters filled with materials like lithium hydroxide, zeolites, or amine compounds bind the carbon dioxide and remove it from the air. But each method has limits. Some must be replaced. Some must be regenerated with heat or vacuum. Each cycle consumes energy, time, and scrutiny. On the International Space Station, similar systems already run. They hum quietly in the background, their fans and pumps as crucial as the station's structure. Yet the ISS has a safety net. If something fails, a resupply capsule can bring new filters. If a system degrades faster than expected, Earth can send updated hardware, or even evacuate the crew if necessary. On Mars, the nearest spare part is tens of millions of miles away. The wrong component wearing out a year early is not an inconvenience. It is a countdown. Oxygen, too, must be manufactured with care. Breathable air is not merely air. It is a precise mixture of gases at a specific pressure. Too little oxygen, and the world starts to dim around the edges. Too much, and the habitat becomes a fire waiting for a spark. On Earth, the atmosphere dilutes our mistakes. On Mars, underground, there is no dilution, only correction or consequence. Oxygen can be generated by electrolyzing water, splitting H2O into hydrogen and oxygen. It can also be produced, more exotically, from the Martian atmosphere itself, cracking carbon dioxide into carbon monoxide and oxygen, the way NASA's MOXIE experiment has already demonstrated on the surface. But each method is a machine with moving parts, seals, catalysts, and thermal cycles. There is no such thing as a simple failure. A failed pump is not a maintenance ticket. It is a gradual thinning of the line between life and vacuum. Then there are the guests that arrive uninvited, trace contaminants. Every material inside a habitat outgasses: plastics, paints, adhesives, clothing fibres, cooking fumes, cleaning products. Even the occupants themselves contribute a slow, steady drizzle of volatile compounds into the air. On Earth, these vanish into a sky 100 kilometers deep. Underground on Mars, they linger in a volume measured in cubic meters. The solution is layers of filters and chemical reactors, activated charcoal beds, catalytic oxidizers, fine particulate filters. They trap, break down, or transform ammonia, formaldehyde, volatile organics, microscopic particulates. Each layer has a lifespan. Each layer must be monitored. Every breath becomes a negotiation, mediated by pumps and membranes. Water tells a similar story, but with a twist that borders on the uncanny. In an underground Martian habitat, you do not simply use water, you share it with your future self. Every shower, every wash, every flush, every drop of condensation on a chilled pipe enters a closed cycle. Humidity condenses on cold surfaces and is collected. Urine is distilled and filtered. Grey water from sinks and showers passes through membranes, filters, resins, and sometimes biological reactors until what emerges is, chemically, water again. The phrase, "yesterday's coffee is tomorrow's coffee," becomes less of a joke and more of a mission statement. We already do this. On the ISS, more than 90% of water is reclaimed from waste streams. The technology works incredibly well, but it works with oversight, with constant replacement of filter beds, with the quiet knowledge that if something clogs, fouls, or fails spectacularly, a cargo ship from Earth can bring new components. If all else fails, the station can be abandoned. In an underground base on Mars, the margins are thinner. Filters accumulate biofilms. Membranes foul with proteins and minerals. Trace contaminants that are insignificant over months become significant over decades. A molecule that slips through a filter once is irrelevant. A molecule that slips through billions of times becomes a new background chemical in your life. Over years, a closed water loop can drift chemically as tiny imbalances accumulate. Managing that drift is an art as much as a science. Sensors must work. Calibration standards must remain valid. People must interpret readings correctly, again and again, through fatigue, distraction, and stress. The problem is not that these systems cannot function. It is that they must function continuously, with almost no tolerance for error. Living underground complicates even the promise of Martian resources themselves. On the surface, thin as it is, Mars offers direct sunlight. Solar panels can spread across the regolith, drinking in the pale light to drive life support, mining systems, and electrolysis. Access to the atmosphere is immediate. Compressors can draw CO2 from the environment and feed it to reactors. Bury your habitat, and you inherit both protection and distance. Distance from light, distance from the cold but usable sky. Power lines, gas lines, and fluid loops must now thread their way through tunnels and boreholes, crossing the boundary between sterile interior and dusty exterior. Every penetration through a pressure hole is a potential leak path. Every line is another thing to monitor, another possible ice plug, another wear point. Extracting water from ice deposits or hydrated minerals involves excavators, drills, heaters, and processing plants. On Earth, if a pump seizes in a mine, the worst case is expensive and dangerous. On Mars, Every malfunction carries the question, how long can the crew survive without this working? The underground location adds complications in subtler ways as well. Dust-laden airlocks open into tunnels. Equipment dragged in from outside brings perchlorates and fine particles that can slowly infiltrate seals and filters. Each attempt to use the planet's resources risks smuggling in more of the planet's hazards. And always, hovering over the engineering, is the human mind. There is a psychological gravity to complete dependence. On a submarine, life is also wrapped in machinery. Air is scrubbed, water is distilled, carbon dioxide is removed. But above, miles of ocean and atmosphere rest on a home planet overflowing with redundancy. Ports exist. Rescue is, in principle, possible. If something fails, somewhere there is a ship, a base, a fleet that can respond. On the International Space Station, astronauts live inside one of the most controlled environments ever built. Yet beneath them is Earth, visible as a luminous disk, rich with oceans and clouds. If life support fails catastrophically, there is at least the possibility of emergency return. The environment is harsh, but the support chain is deep. Underground on Mars, the chain is thin and stretched across space. Outside the rock is not an ocean or a sky, but a thin, nearly airless atmosphere at a temperature that freezes unprotected metal and flesh. There is no emergency supply ship that can arrive tomorrow. There is only what is already there and the time it will take for the next window of alignment between planets. Knowing this is not an abstract fact. It becomes a feeling. The quiet hum of fans at night is no longer just background noise. It is a reminder. A pump cycling on and off is not just machinery. It is the sound of liquidity itself being maintained against a world that would happily turn every drop to ice. For some, this might be bearable, even inspiring, a test of skill, resilience, and cooperation. For others, the unbroken awareness that every breath, every drink, every small comfort depends on systems that must never fully rest may weigh heavily. It does not mean such a life is impossible. It means that the underground sanctuary is not a natural refuge, but a carefully constructed bubble of Earth-like conditions fighting entropy and time in a hostile world. In that sense, the nightmare is not monsters in Martian caves. It is the relentless, unromantic detail of survival. Valves, filters, sensors, backups, all of them operating in a loop that must hold night after night, year after year. Beneath the surface, in the stillness of Martian rock, the air and water are not gifts. They are agreements, temporary, conditional, maintained by vigilance. And as we imagine sleeping in such a place, far from Earth, we are left with a quiet question. How long can a closed loop stay closed before it starts to close in on us? Beneath the rusted plains of Mars, we imagine safety. Rock above us, dust between us and the radiation, a shelter carved into ancient lava tubes, hidden from the storms that scrape across the surface. In drawings and digital renders, these Martian caves look calm, almost cozy, washed in soft artificial light. But the moment a human steps inside and closes the habitat door, another kind of storm begins. Not of dust and ice, but of biology. Our bodies were written by Earth. Every cell, every heartbeat, every sleeping moment carries the imprint of one gravity, one day-night cycle, one sky. On Mars, especially underground, that script begins to unravel. Mars pulls with only 38% of Earth's gravity. At first, this feels like a miracle. Heavy tools become light. A person who struggles to climb stairs on Earth might bound up them with ease. But our bones and muscles are not just passive supports. They are negotiated agreements with gravity. On Earth, Every step tells your skeleton, stay dense, stay strong. Every time your heart pushes blood up from your feet, your cardiovascular system is reminded of the work it must do. In 0.38 grams, that conversation changes, slowly, silently. On the International Space Station, astronauts in near weightlessness can lose measurable bone density in just a few months, even with rigorous exercise. Their muscles shrink, especially in the legs and back, the very places that once fought Earth's pull with every movement. The heart, no longer working against full gravity, can remodel itself, becoming less efficient when returned to normal weight. Martian caves are not weightless, but they are underloaded. A colonist who spends years there lives in a world where everything is just a little too easy to lift, a little too gentle on the joints. The body responds to this new normal as if it were a kind of long, slow rest. Bones might thin, muscles might soften, tendons could weaken. The risk is not just frailty, but a hidden dependence on Mars itself. Over time, returning to Earth's full gravity might become as dangerous as leaving it once was. We could build gyms deep underground, tether ourselves to treadmills, spin in centrifuges that simulate full gravity for a few hours a day. Yet here, too, questions remain. How many hours are enough? Which muscles need Earth-like strain, and which can adapt to Martian ease? Is there a threshold below which the body simply begins to rewrite itself into something that is no longer fully Earth-human? In the dim tunnels of a Martian habitat, another quiet struggle unfolds, not with gravity, but with time. On Earth, light and darkness sweep over us in a predictable rhythm. The sun rises, the sky brightens, evening settles, and night invites us to sleep. This pattern is not just scenery, it is a metronome for our biology. Deep in the brain, the suprachiasmatic nucleus, our master clock, takes its cues from sunlight. Hormones like melatonin and cortisol rise and fall with the day. Temperature, hunger, alertness, even mood, all drift in this invisible tide. Underground on Mars, there is no dawn and no dusk. The outside world runs on a Martian soul, about 24 hours and 39 minutes long, but thick rock blocks every photon. Inside, artificial lights create a new sky, one that can be dimmed, coloured, and timed by computers. In theory, this can mimic Earth's day. In practice, the subtle differences may matter. In Antarctic research stations, where winter brings months of darkness, crew members often report disrupted sleep, drifting bedtimes, and a sense that days blur together. On submarines, where sailors live under constant artificial light, careful planning is needed to keep circadian rhythms from sliding into disorder. On the ISS, even with the pattern of 16 sunrises a day, astronauts depend on controlled lighting to stabilize their internal clocks. In a Martian cave, the risk is a kind of temporal disorientation. If lights are not perfectly tuned, if schedules slip, if long emergencies or tasks push sleep aside, the body's rhythms may begin to rebel. People might feel tired, but wired, hungry at odd hours, unfocused, emotionally fragile. Over months and years, chronic circadian disruption can affect metabolism, cardiovascular health, and mental well-being. We think of living underground as protection from the environment. But in doing so, we remove one of biology's oldest environmental signals, the sky itself. Far below the Martian surface, another frontier is tested, the human immune system. Our defenses against disease are not static walls, but living responsive systems deeply influenced by stress, isolation, and confined spaces. On the ISS, astronauts often show changes in immune function. Some aspects rev up, Others quiet down. Dormant viruses, like those that cause cold sores or chickenpox, can reactivate under spaceflight stress. In Antarctic stations, crews experience higher rates of certain infections, especially early in overwintering periods. Even on long submarine patrols, where external germs are carefully controlled, changes in immunity and inflammation can be measured. A Martian cave colony would combine elements of all three: isolation from the outside world, recycled air, limited new microbial input, and the persistent, low-level stress of living in a fragile habitat. Every cough, every minor cut, every shared surface becomes more significant in a small, closed ecosystem. The immune system, constantly negotiating between underreaction and overreaction, may find this environment unfamiliar. Reduced gravity could alter how immune cells move and communicate. Stress hormones might nudge the system toward chronic, background inflammation. Over years, this could shape not just how colonists handle infections, but how their bodies age. And then there is the question that reaches even deeper. How does life begin in a place like this? On Earth, human development has unfolded under the steady pull of 1G for billions of years of evolutionary history. Embryos form, cells divide, organs assemble themselves according to a pattern that assumes a certain force always points down. Blood flows, bones mineralize, the inner ear calibrates its sense of up and down in the first months and years of life. On Mars, at 0.38 grams, in an underground habitat lit by LEDs and shielded from cosmic rays by rock and metal, that foundational assumption disappears. We do not yet know how a human embryo will respond to long-term low gravity. Will cells migrate correctly? Will the developing heart and vessels learn to pump in a weaker field? Will the vestibular system, the inner sense of balance, adapt gracefully or be confused from the start? Animal experiments in space have offered glimpses: altered muscle development, changes in brain structure, differences in how bones grow. But these are hints, not answers. The full story of human reproduction and childhood in low gravity has never been told because it has never been lived. In a Martian cave, the first generation born away from Earth would not just be visitors. They would be native to that world, shaped by it in ways we can only imagine. Their biology might subtly diverge from ours, not in a single dramatic leap, but in thousands of quiet, accumulated differences, written into bone density, lung capacity, balance, and even psychology. For them, Earth's gravity might feel not like home, but like an overwhelming weight. All of this unfolds against a backdrop that is not measured in milligrams or micro-Roentgens, but in something more fragile: the human mind. Permanent underground existence on Mars is, at its core, an experiment in being forever inside. No open sky, no distant horizon, no wind across the face unless it is generated by a fan. The cave becomes the world. Every hallway, every room, every light panel is known, mapped, predictable. We have small windows into what this feels like. In Antarctic winter, crews can go months without seeing the sun. In some stations, the same corridors blur into a mental loop. Submarine crews can be submerged for 90 days or more, with no windows, no real-time view of the sea around them. On the ISS, astronauts often describe Earth as an emotional anchor, visible with every pass. In a Martian cave, even that anchor is gone. Psychologists who study isolated and confined environments speak of third-quarter syndrome, a slump that can emerge partway through a long mission. The initial novelty has faded, the end is not yet in sight, and monotony deepens. Irritability grows. Small disagreements feel larger. Sleep can become shallow. Dreams become vivid. In an underground Martian habitat, this psychological landscape would be the everyday terrain. The soundscape of humming machinery, the constant awareness that beyond the walls lies not a walkable park or a safe ocean, but rock, vacuum, and lethal cold. Some people might find deep comfort in the routine, the enclosed safety, the tight-knit community. Others might feel a longing that no virtual window can quite satisfy, a quiet ache for clouds, for trees, for a horizon that is not made of steel and stone. To live well in such a place, we would need more than engineering. We would need rituals that mark time, spaces that feel different from one another, ways to invite randomness and beauty into a controlled environment. Perhaps gardens undergrow lights, art projected on walls, communal meals that become small festivals against the red darkness outside. The human body in Martian caves is not merely under threat. It is negotiating a new contract, with gravity, with light, with immune memory, with the future of our species. Some parts of this contract we can anticipate, others remain blank spaces, waiting to be filled by real lives, real risks, real adaptation. Biology does not yield easily. It rebels, resists, and then, slowly, sometimes, it rewrites itself. In the shadows of Martian lava tubes, that rebellion would not be loud. It would be measured in blood tests, in sleep logs, in the quiet journal entries of people who lie awake under an artificial sky, listening to the hum of air recyclers and wondering how long it takes for a human heart to truly belong to another world. On Earth, almost everything we build is the result of practice. Bridges are tested. Airplanes are tested. Even the chair you sit in has been modelled, stress-tested, and refined over decades of tiny failures and quiet improvements. On Mars, underground, we do not get that luxury. We are asked to design a home for human beings, in a place no human has ever stood, carved into rock no human has ever touched, under a sky no human has ever breathed beneath. We can simulate, we can guess, we can hope, but a true rehearsal, that will only happen on opening night. We can build analog habitats in deserts and in polar ice, bury facilities beneath sand, cool them, seal them, even pump in artificial atmospheres. We can dim the lights to mimic Mars's distant sun. We can expose materials to radiation in labs. All of this helps. It sharpens our estimates. It trims our uncertainty, but it does not erase it. On Earth, our tests happen in a world wrapped in a thick magnetic field, with a dense, warm atmosphere pressing gently on every surface. We do not yet know how a buried dome will truly age in Martian darkness. We cannot perfectly reproduce the low gravity, the thin, nearly airless atmosphere, the constant fine dust pulled by feeble winds and electric charges into every microscopic crack. A habitat on Mars is not a building in the way we think of buildings. It is more like a life support machine that happens to have rooms. Every wall is doing something, holding pressure, holding heat, holding back radiation. The engineering challenge is not just to make it work once, but to make it work every hour of every day, for years, while an alien planet slowly, patiently tries to unmake it. The materials we send will be asked to endure a kind of weather that barely exists on Earth. Mars can swing from a daytime just below freezing to a nighttime deep in the Antarctic range, over and over again, with almost no insulating blanket of air to soften the blow. Metal contracts, plastics stiffen, rubber seals harden, then crack. On Earth, those cycles are slowed, dampened, softened. On Mars, they are sharp and direct. A buried habitat is protected from some of this, but not all. Pipes run from inside to outside. Cables pass through walls. Airlocks open and close. their hinges and seals experiencing thousands of mechanical heartbeats in a place far colder than they were ever truly meant to be. Then there is the radiation. We often imagine that being underground solves it, that a few meters of regolith turn Mars into a safe, quiet cocoon, and it helps. Mass is a shield, and rock is mass. But radiation is not a single thing. It is a spectrum of high-energy particles, solar flares, galactic cosmic rays. Some are stopped, some are slowed, some fragment, producing showers of secondary particles within the very walls meant to protect you. Over time, these particles whisper through materials, rearranging atoms, breaking bonds. Plastics embrittle. Electronics slowly accumulate damage in their tiny circuits. The habitat may be still, but the physics around it never sleeps. We can irradiate materials on Earth and model the damage, but the true pattern, the way all these stresses layer together in real Martian time, will only reveal itself after the habitat is occupied. And Mars adds its own quiet chemistry. The dust you dig through to form your shelter may be laced with reactive perchlorates, with superfine particles that behave more like smoke than sand. Seals and filters and air ducts breathe that contamination in day after day. Some materials will shrug it off. Others may unexpectedly corrode, swell, or break down. In this environment, every system becomes a promise we must keep indefinitely. Air has to be scrubbed, carbon dioxide removed and recycled, oxygen monitored and replenished. Water must circulate through pipes, filters, tanks, and condensers. Heat must be moved from where it is generated to where it is needed, without simply drifting away into the surrounding rock. In a house on Earth, we accept that things fail. The heater stops. The pipe leaks. The light flickers. We call a technician. We schedule a repair. The world around us remains stable while we figure it out. On Mars, underground, failure is not an event. It is a clock. When the air recycler pauses, when the CO2 scrubber clogs, when the main power inverter complains, the countdown begins. There is no outside air waiting just beyond the door. There is no safe temperature if the heaters die. The habitat is an artificial island of Earth in an ocean of cold, thin, toxic air. Maintenance becomes a way of life. Every pump, every valve, every fan and sensor and circuit board has a lifetime, a curve that gently slopes from new to worn to failed. In the design phase, we draw these curves on charts, we assign safety margins, we add redundancy, 2 pumps instead of 1, 3 methods to generate oxygen instead of 2. Yet redundancy is not magic. Every extra system you add must itself be maintained. Every backup has its own failure curve. Over years, even dormant systems age. Lubricants separate. Batteries self-discharge. Seals that were installed on Earth, in humidity and warmth, gradually adapt to a new baseline of dryness and chill. So, when something breaks, and sooner or later, something will, what then? On Earth, replacement is simple. A supply chain stretches around the globe. Factories run, ships move, trucks deliver. A part that fails in the Arctic might have its twin manufactured in a temperate city, flown halfway around the world, and installed within days. On Mars, every spare part is a choice made years in advance. Every kilogram of tools, bearings, circuit boards, replacement filters, sealants, and adhesives competes with food, fuel, scientific instruments, and shelter in the launch manifest. Do you pack another air pump or more medical supplies? An extra valve assembly or a spare suit visor? In time, settlers may build workshops and small factories on Mars. 3D printers may hum in underground rooms, extruding plastic housings and simple metal parts. Dust might be melted into bricks, or sintered into pipes. But high-performance electronics, specialized alloys, precision components, these will remain difficult to produce in the early decades. A failed microcontroller or a cracked pressure sensor may hinge on a single, irreplaceable chip. When that chip fails, the question becomes not just, how do we fix this, but what can we do without? Habitats may have to be rerouted, systems downgraded, non-essential functions shut off, just to preserve the essentials: air, water, warmth. Life may not end in a dramatic catastrophe, but in a slow narrowing of comfort, a steady shrinking of what is possible. And over all of this hangs a delay. On Earth, when something confuses us, we ask for help. We call a friend, a parent, an expert. On the International Space Station, astronauts can speak to mission control almost in real time. Engineers can watch telemetry and say, "Try this. Now that, adjust that setting." On Mars, a question asked in crisis may not receive an answer for up to 20 minutes. Another 20 for your reply to return. In the time it takes for a single round-trip conversation, an overheating battery could ignite. A leaking air duct could drain a reserve tank. A glitch in a pressure valve could cascade into a larger failure. So the people living underground will become not just inhabitants, but their own emergency response teams, their own engineering departments, their own last resort. Checklists and training will help. Simulators and practice runs will help. But in the end, decisions in a true emergency will be made in silence, with the comforting voices of Earth still trapped in the thin beam of a radio signal gliding through space. All of this just to keep the lights on. Energy is the invisible river that must flow through every part of an underground Martian home. Heat, light, air circulation, water recycling, mining, tunneling, communication. All of it is just electricity with different names. On the surface, solar panels drink in the faint Martian sunlight. But that light is weak, less than half the intensity we enjoy on Earth. Dust slowly veils the panels. Seasons tilt the planet, changing the angle of the sun. And sometimes, whole planet dust storms rise, dimming daylight to a reddish twilight for weeks or months. For an underground colony, this is more than an inconvenience. It is a question of survival. Heating a subsurface habitat against the cold of the surrounding rock, running lights to mimic day and night, keeping pumps and filters and computers alive. These are not optional. Nuclear reactors may offer a steadier, deeper well of energy, humming away in their own buried chambers, decoupled from weather and dust. But they too age. Turbines wear. Fuel rods must be managed. The engineering task is not only to generate enough power, but to do so with systems that can be repaired, inspected, and in the end, replaced, far from the world that built them. We often picture the underground city on Mars as quiet and permanent, carved once and then simply occupied. In reality, it would be more like a living organism, constantly healing small wounds, constantly shedding old parts and growing new ones. A breathing machine whose every component rests under a question mark. How will this behave here over time? In that uncertainty lies both the danger and the strange allure of the idea. To build underground on Mars is to practice a form of engineering we have never truly attempted before. Designing for a world we cannot fully test, and trusting that when the unknowns finally reveal themselves, the people there will have just enough knowledge, just enough tools, and just enough time to adapt. It is a dream of shelter at the edge of what we can predict. A promise written in equations, shipped across millions of miles, and finally tested not in simulations or laboratories, but in the quiet, red-lit halls of a buried home on another world. Deep beneath the Martian surface, the world is quiet. The storm-torn sky is sealed above layers of rock, regolith, and ice. Inside the habitat, the air is still, filtered, recycled, measured down to the last molecule. On paper, this is safety. Thick walls shielding you from radiation, micrometeorites, and the thin, hostile atmosphere outside. But safety on Mars is not a feeling. It is a calculation. And sometimes, the math turns against you. On Earth, escape is almost always up. Out a door, down a stairway, through an emergency exit glowing in green. In a building, a mine, a submarine, there is always an assumption, however fragile, that somewhere above you lies open air, a sky, a place where you can breathe without machinery. On Mars, underground, that assumption is inverted. Above you is vacuum-thin air laced with dust and perchlorates, temperatures that can plummet far below freezing, and radiation that never truly sleeps. Here, the surface is not a refuge. It is just a different kind of danger. Imagine you are lying in your bunk in a cavernous lava tube habitat. The rock around you has stood for millions of years, sculpted by ancient volcanic flows. Your eyes close. Systems hum quietly, like the breathing of the base itself. Then, somewhere in the distance, an alarm begins to pulse. Not a gentle chime, a sharp, insistent tone that slices through the dim light. A fire has started. Fire in a pressurized habitat is not just a hazard, it is a paradox. You need oxygen to survive. Fire needs oxygen to grow. Every breath you take, every tank you store, is also fuel for a catastrophe. On Earth, a fire department can surround a burning building. They can sacrifice walls, flood rooms, break windows. On Mars, you cannot call anyone. There is no one else on the planet. The fire is contained within the same thin envelope of pressure that contains you. If a compartment fills with smoke, there is no stairwell leading to fresh air, no window. You can smash open to gulp the wind. There are only more doors, more seals, more tunnels of artificial atmosphere. To outrun the fire, you must move through the very thing that makes its spread possible. Shared air, shared pressure, shared life support. Depressurization is quieter, but more merciless. A micrometeorite fractures a buried conduit. A seal ages poorly. A valve fails. Somewhere pressure begins to fall. Perhaps slowly at first, perhaps all at once. The habitat does not groan, does not crack like a ship at sea. The numbers simply start to drift on a screen. 101 kilopascals. 90. 80. In a Mars base, every cubic meter is engineered. There are no outside spaces you can rush into to escape a leak. If a major section loses pressure, your choices are limited. Seal it off and abandon everything inside, or try to repair it from another pressurized zone. Each emergency door that slams shut might save the colony, but it also might strand someone behind it. In underground tunnels, those decisions can be measured in seconds, not minutes. Now imagine a different kind of emergency. A colonist collapses during a routine task. Chest pain, unconsciousness. On Earth, this story has a familiar rhythm. Call an ambulance, rush to a hospital. Teams of specialists, equipment, blood banks, operating rooms waiting under bright white lights. On Mars, the nearest hospital is tens of millions of miles away. The best you can do is whatever you packed in the payload of a few rockets years ago. In an underground habitat, even reaching the surface may be slow. Elevators, pressure locks, narrow corridors designed to minimize volume and mass. There is no helicopter medevac, no life flight roaring through the night. If the medical bay you have is not enough, there is nowhere else to go. The question is not, how fast can we get you to care? It is, did we guess right about what we'd need before we ever left Earth? The distance from rescue on Mars is not just physical, it is temporal. Depending on orbital alignment, a round-trip mission to Earth and back could span years. Even communication is delayed. A distress call sent to mission control on Earth arrives between 4 and 24 minutes later. Advice and instructions, no matter how expert, are never immediate. In the most critical moments, colonists are not just the crew, they are their own ground control. To compensate for this isolation, engineers turn to redundancy. Every critical system, air, water, power, communications, must have backups, and then backups for the backups. On the International Space Station, redundancy is already a guiding principle. On Mars, it becomes a philosophy of survival. But redundancy has weight. Extra filters, extra pumps, extra cables, spare suits, backup medical supplies, duplicated life support modules, emergency habitats sealed deep within the cave. All of it must be either launched from Earth at enormous cost or manufactured in situ with technologies that are still experimental. Each kilogram of just in case is a kilogram that cannot be something else. Every safety margin is paid for in fuel, time, and budget. Designers imagine branching tunnel networks, multiple routes between key sections of the base, fire breaks, pressure doors staggered like locks on a canal, separate air supplies for different zones, independent power loops that can isolate a short without darkening the entire colony. In concept, these are familiar ideas, borrowed from submarines, polar stations, and nuclear facilities. In practice, on Mars, every added corridor is not just architecture. It is atmosphere that must be pressurized, monitored, heated, and defended against leaks. The escape problem, then, is not simply about leaving the underground. It is about having anywhere to escape to that is safer than where you already are. An emergency shelter closer to the surface might shield you from a fire, but expose you to more radiation. A secondary habitat further down the tube might offer safer pressure, but take longer to reach in a crisis. Every refuge has trade-offs, and none of them lead to a blue sky. Beyond the physical risks lies a quieter, deeper challenge, the knowledge that there is no cavalry coming. On Earth, even in the most extreme environments, there is usually a chain of aid. Rescuers, coast guards, specialized miners, disaster response teams. Even if help is delayed, the idea of help exists. On Mars, especially in the early decades, that idea will be more fragile. Colonists will live knowing that any rescue, if possible at all, must come from within the same small group of people who are already there, sharing the same risks. Psychologists studying analog missions in Antarctica or simulated Mars bases notice something subtle. People behave differently when they know, deep down, that someone could fly them home if things truly went wrong. Remove that last line of retreat and stress changes flavor. It no longer spikes only during emergencies. It becomes a constant background hum, a low-frequency awareness that the margin for error is thin and permanent. Underground, in a Martian cave, this awareness may be amplified. Rock above you, regolith outside, a horizon you cannot walk toward. The base becomes not just your home, but your entire universe. Any alarm, any malfunction in the pumps or the scrubbers or the seals carries an extra psychological weight. There is nowhere else. Current mission plans try to grapple with these realities, but they are, by necessity, incomplete. Space agencies and private companies propose phased approaches. Early missions would likely be small, semi-temporary habitats, more like advanced expeditions than permanent towns. Redundancy would be built in where possible, multiple landers, separate habitats connected by pressurized tunnels, independent life support stacks. Emergency rovers might act as mobile lifeboats, able to sustain a handful of people for days if a main habitat fails. Some concepts imagine safe rooms carved deeper into rock, stocked with weeks of supplies, capable of sealing independently if the primary base is compromised. Others suggest distributed settlements, several smaller habitats spread across a local region so that one can, in principle, assist another. But the distances between them will not be like crossing a hallway. In the early eras of Mars, they will be like crossing deserts. Any help sent will be travelling through the same vacuum-thin air, in the same fragile vehicles, with the same limited tools. In glossy animations, evacuation looks smooth. Airlocks cycle flawlessly, corridors glow gently, rovers glide away under a salmon sky. Reality, if it comes, will be more uncertain. Dust may obscure paths, doors may stick, people under stress may make mistakes. While engineers model every failure mode they can imagine, no one can anticipate them all, especially in an environment that has never hosted humans before. And yet, understanding the escape problem is not an argument against going. It is a lens, a way to see clearly what survival underground on Mars would truly demand. Not just thick walls and clever designs, but a rethinking of what safety means when the nearest open sky is not friendly and the nearest help is a blue star hanging far away in the darkness. In that distance, in that separateness, lies both the greatest risk and the deepest question. If we choose to live in such a place, knowing that underground can be both shelter and trap, what does that say about our willingness to venture, to endure, and to accept that some journeys offer no easy exit, only the promise of learning how to stay? We have spent a long time in the shadows, listing all the ways Mars quietly says no. But it is worth pausing here, in this dim red twilight, to listen for the ways it might one day whisper yes. Because for all its brutality, Mars also offers something precious, a world that is not yet written. And beneath its battered crust, many see not a tomb, but a blank page. If we look at the underground dream from its strongest side, the argument becomes clearer. Rock is a shield. On Earth, deep mines and mountain tunnels mute cosmic rays and solar storms almost entirely. On Mars, even a few meters of regolith or rock could cut radiation to levels closer to what astronauts endure on the International Space Station. Still harsh, still dangerous over decades, but survivable with careful planning. Temperature is another ally. The surface of Mars swings wildly from day to night, its thin air unable to hold heat. But just a few meters underground, the world calms. Temperatures change slowly, like the deep layers of an ocean. For engineers, that stability is a gentle gift. Fewer extremes, fewer cycles of freezing and thawing tearing structures apart. Dust storms, too, lose their teeth below the surface. No howling winds, no sandblasted solar panels, just a faint, muffled rumble like distant surf, as fine grains sweep across a roof of rock that never blinks. For some, those three facts, radiation, temperature, dust, are enough to make the underground seem inevitable. If we're to stay on Mars for more than brief visits, they argue, we will have to go down. And if technology continues its slow, relentless march forward, the tools we bring with us could change the story even further. Imagine robots that do not look like the delicate machines we launch now, but like tireless dust-coated miners. Swarms of autonomous diggers and tunnelers landing years before any human, boring into cliffs and lava tubes, printing structural supports from Martian rock itself. What feels impossible for a handful of astronauts with shovels becomes routine for 1,000 machines that never sleep. Inside those carved caverns, life support systems might become less brittle than the versions we imagine today. closed-loop habitats on Earth are already being tested, recycling air, water, even nutrients in slow, careful cycles. They fail, they are redesigned, they fail again, and each failure becomes a lesson. 50 years from now, those lessons may add up to something that feels less like an experiment and more like an ecosystem. Artificial, but resilient. Perchlorates in the soil, so toxic to our cells now, might be tamed by microbes we engineer to eat what we cannot. Living filters, turning poison into fertilizer, turning sterile dust into something quietly alive. The tools of synthetic biology, which today live mostly in laboratories and code, could one day travel in vials and prints, unfolding into self-sustaining cleaning crews under the dim Martian sun. None of this makes Mars gentle, but it nudges it from impossible towards difficult, and difficult is a landscape humanity knows well. Still, even in the most optimistic visions, very few people imagine a future where we vanish entirely into the rock. What begins underground may not stay there. Hybrid worlds start to appear. Picture a habitat anchored into the wall of an ancient lava tube. Living quarters stretch deep into the cooled basalt, where radiation is a memory. But at the tube's mouth, a transparent dome rises, thick, layered glass or advanced composites, perhaps covered in smart materials that darken or brighten with the angle of the sun. Inside the dome, green erupts against the rust-red landscape. Hydroponic towers, algae pools, compact orchards, adapted to the thin, filtered light. Most people sleep, work, and repair systems in the quiet safety underground, but they walk to the greenhouse for something else. Color, smell, the soft rustle of leaves, a small patch of open volume, where gravity is still Martian, but the view offers a slice of sky. Some concepts place rotating habitats on the surface or just above it, pressurized rings that spin slowly to generate artificial gravity closer to Earth's. Perhaps the core of such a structure is buried or banked under regolith for shielding, while the rotating section rises like a wheel partially in the ground, half protected by rock, half reaching into the light. In these hybrid designs, Mars becomes layered, buried corridors for safety, surface domes for agriculture and morale, rotating segments for long-term physiology. No single solution wins. Together, they form a patchwork of compromises. If we stretch our imagination further along the timeline, these compromises shift with each century. In the next 50 years, anything on Mars is likely to be small, cautious, and extremely expensive. Short missions, a handful of people. Underground spaces will be more like emergency shelters and research modules than cities. Safe rooms carved into rock, not yet the vaulted caverns of science fiction. In 100 years, if we maintain the will and resources, we might see semi-permanent outposts, multiple bases linked by tunnels, shared supplies, and redundant systems. Some sections still experimental, others quietly ordinary. Kitchens, sleeping quarters, small communal rooms where the novelty of Mars has faded into daily routine. The underground becomes less a daring experiment and more a practical fact of life. 200 years from now, the picture becomes misty, more art than forecast. By then, humanity's relationship with off-world living could have transformed entirely. If advancements in materials, energy, robotics, and biology converge, Martian caverns could be sculpted with the same confidence we carve metro systems on Earth. There might be wide, pressurized galleries, artificial rivers, cycling water through underground parks, even carefully managed open shafts where, on certain days, sunlight is allowed to pour down like a distant, sacred visitor. Or, just as possible, Mars might remain sparsely populated, visited, studied, maybe mined, but never widely settled. Our main homes beyond Earth could be elsewhere, because as we way underground Mars, other paths rise into view. The Moon waits much closer, a 3-day journey instead of months. Its gravity is weak, its nights long and freezing, but it offers an invaluable advantage: proximity to home. Lunar lava tubes, some enormous by terrestrial standards, could serve as a nearby rehearsal stage for everything we dream of doing on Mars. Sealing caverns, managing dust, building closed loops, all under the watchful eye of a planet just overhead in the black sky. Beyond the Moon, another idea floats quietly but persistently. Orbital habitats, not worlds, but worlds we build. Rotating stations, vast cylinders or rings where gravity is created by motion, not mass. In these habitats, radiation shielding can be layered with water, rock, or manufactured materials, adjusted over time. Day-night cycles are programmable. Atmospheres are blended, not inherited. Instead of adapting ourselves to a planet's indifference, we sculpt the environment to match us, at least as closely as physics will allow. Some thinkers see these orbital homes, not Martian caves, as the true future of human space living. Mars, in this view, becomes a place we visit, not a place we bury ourselves in. And yet, the dream of walking under that pink-orange sky, of seeing Phobos rise like a ragged stone lantern above the horizon, persists. The value of this dream is not measured only in feasibility. It lives in something more fragile, the human urge to step beyond the known, even when the ground is rough and the air is thin. We go because the universe is not empty. It is filled with questions. Can we carve a home in rock that has never known life? Can our machines keep us alive in a place that does not care whether we breathe? Underground on Mars, the answers are not yet kind, but they are not final. Somewhere between rock and sky, between caution and curiosity, our future in the cosmos is still being written. Line by line, habitat by habitat, dream by dream. Long after the engineering diagrams fade from the screen and the calculations settle into silence, one question remains, hovering over the red horizon like a second dawn. Why this world? Why Mars? Of all the places we could imagine living, we choose a frozen desert bathed in radiation, with a sky the colour of dried blood and air too thin to breathe. The logic, as we've seen, is fragile. The challenges are immense. And yet, Mars persists in our imagination with a kind of quiet gravity of its own. Part of this pull is ancient. For as long as humans have looked up, Mars has looked back. A wandering red star that moves against the fixed tapestry of the night. To early astronomers, its erratic path and shifting brightness hinted at something different, something restless. Not just a point of light, but a world. Over centuries, our stories gathered around it. Ares and war, omens and prophecies, then canals and civilizations in the imaginations of 19th century observers who thought they saw straight lines on its surface, carved by intelligent hands. We now know those canals were illusions, tricks of optics and expectation, but the feeling they created stayed behind. Mars was not just a rock. It was a destination. In the quiet of the night, that idea still hums beneath the science. Mars is the planet that feels like a mirror, not because it resembles Earth, but because it shows us a version of ourselves we do not yet know. A civilization that has solved problems so difficult that living underground on a hostile world becomes not just possible, but routine. This is the heart of the backup humanity dream. The idea that somewhere, under a Martian sky, there will be a second archive of our species. a redundant copy of Earth's story, written in basalt and regolith instead of oceans and forests. If disaster comes, whether from our own hands or from cosmic chance, then humanity will not be a single fragile line, but a branching path. It is a comforting thought, the lifeboat at the edge of the cosmic ocean. But embedded in that vision are quiet assumptions that rarely make it into the slogans. We assume that we will become capable of building entire sealed ecosystems underground on another planet before we manage to keep one intact on the world that already supports us. We assume that a society able to terraform deserts, recycle every molecule of air, and sustain life inside rock will somehow fail to prevent climate collapse, war, or ecological loss here at home. We assume, in other words, that it is easier to start over on Mars than to heal Earth. When the mind is calm and the numbers are clear, that assumption begins to flicker, because the technologies that Mars demands, perfect recycling, closed-loop agriculture, robust energy systems that work without compromise, are exactly the tools that would make Earth more livable, not less. Every breakthrough that keeps a human alive 100 meters below Martian rock would work even better under a blue sky, with oceans, plants, and a protective magnetic field already doing half the job. If we can one day master life on Mars, it is difficult to imagine that we cannot also master life on Earth. So the question shifts. Are we really dreaming of escape? Or are we dreaming of competence, of becoming a species that can take care of anything, anywhere? For many, Mars is not an abandonment of Earth, but an expression of faith in what humans can become. A symbol that we might someday be wise enough, careful enough, and patient enough to carry life beyond the cradle without dropping it. Still, there is a quieter, more uncomfortable possibility that the backup planet story can sometimes serve as a lullaby, a narrative that lets us delay hard choices here because we imagine a brighter, redder future elsewhere. If we are not careful, Mars can become a story we tell ourselves to soften the urgency of our own century. In the dim glow of that thought, another perspective rises. Exploration has always walked beside risk, not as a replacement for responsibility, but as a companion to it. When our ancestors crossed mountains, oceans, and frozen land bridges, they were not fleeing their world so much as expanding their understanding of it. Each impossible journey made the next one seem slightly less impossible. Mars fits that lineage, not as a sanctuary, but as a frontier of knowledge. Attempting to live underground on Mars forces us to wrestle with questions that are larger than any one planet. How do closed systems behave over decades? What happens to humans when their environment is entirely artificial, down to the last molecule? How do we design societies when every resource, every cubic meter of space is counted? These are not only Martian questions, they are Earth questions, simply turned up to their highest setting. In trying to solve problems that seem almost absurd in their difficulty, we expose the hidden limits of our understanding. Sometimes we fail publicly. Sometimes we discover quiet, unexpected truths. That some crops thrive under dim, narrow-spectrum light. That certain materials outgas slowly for years, poisoning the air. That humans adapt better to confinement when they feel they have genuine purpose, not just survival. The value of such attempts is not always in their success, but in the new ways of thinking they force upon us. A failed habitat design may still teach us how to manage air in submarines, in skyscrapers, in disaster shelters. A psychological study meant for Martian crews may help isolated communities on Earth. Even the act of carefully modeling how a colony might die becomes a lesson in how not to let society stumble in the dark. In this way, Mars becomes a distant mirror not only for our ambitions, but for our humility. There is a balance to be found somewhere between cynicism and blind faith, between saying Mars will save us and Mars is a pointless fantasy. Reality, as usual, is quieter and more complex. We can acknowledge that colonizing Mars is harder than most stories admit, that the underground refuge is not a simple answer to planetary problems. We can also accept that the dream itself has value, not because it guarantees our survival, but because it challenges us to understand what survival truly requires. To dream of Mars is to place a question mark at the edge of our maps. Can we become a species that plans not just for quarters and years, but for centuries? Can we build systems so resilient that they endure not just on the best of days, but on the worst of worlds? Can we learn to create environments that are not merely habitable, but humane, even when nature offers us nothing for free? As you imagine those underground halls carved into Martian stone, the humming life support systems, the slow rhythm of recycled air, the artificial sunrises glowing on cavern walls, it may help to see them as reflections of deeper choices. Every pressure door, every farm module, every line of code keeping that outpost alive is a commitment to complexity, maintenance, and care. It is a promise that someone will be there, decade after decade, to keep watch over a fragile patch of ordered air in a universe that prefers disorder. In that sense, the real question is not why we dream of Mars, but what those dreams ask of us. Do they invite us to turn away from our own world, or to look at it more closely? Do they tempt us with escape, or remind us that any future, on any planet, must be built with the same patient attention to detail, the same willingness to learn from failure, the same honesty about risk? Mars is not a verdict on humanity. It is an invitation to think longer, deeper, and more carefully about what it means to carry life with us wherever we go. Some dreams are not meant to be instructions. They are meant to be lenses. Through them, we see our present more clearly, our limits, our strengths, our unfinished work, and in the red dust of that distant world, beneath imagined ceilings of stone, we may glimpse not the end of Earth's story, but a reminder. Before we can live well anywhere else, we must understand what it truly takes to live well here. We began with a simple idea. If the surface of Mars is too harsh, we will go beneath it, into lava tubes, buried habitats, sheltered caverns carved from ancient rock. Down there, many hoped, the problems would soften, radiation would fade, dust storms would mute, and Mars would finally become a place we could quietly endure. But as we followed that dream underground, we discovered that the shadows do not erase the challenges. They rearrange them. Radiation does not vanish at the first layer of stone. It thins, it scatters, but the invisible storm still seeps in from above and below, from cosmic rays and secondary particles born in the very rock that shelters us. The ground that cradles our habitat is also laced with chemicals that tear at our lungs and cells, perchlorates and reactive dust waiting at every seam and airlock. Air and water do not spring naturally from the walls. They must be built, recycled, guarded in loops that never truly rest. Every breath becomes an engineering problem. Every glass of water a calculation in a closed system that cannot afford forgetfulness. Even our bodies, which evolved for open skies and one full Earth gravity, do not surrender easily to the Martian underworld. Muscles, bones, and minds protest the dim light, the altered day, the silent pressure of a world that does not share our rhythms. The underground is quieter, safer in some ways, yet it can press on the psyche like a second atmosphere. And then there is the trap we do not like to name, the escape problem. To live beneath the surface is to add layers between ourselves and any path home. Extra doors, extra tunnels, extra minutes when minutes might matter most. Safety gains a new vulnerability. Distance from the open sky. None of this is meant as a verdict against the dream of Mars. It is an invitation to see it more clearly. When we slow down and look closely, the fantasy does not have to shatter. It can become something richer, more honest. A dream that admits the weight of radiation, toxic soil, failing pumps, and fragile minds, and still asks, knowing all this, what would it take to go anyway? Asking hard questions is not an act of cynicism. It is a kind of respect. Respect for the people who might one day step into those caverns. Respect for the engineers who will design the walls between life and vacuum. Respect for the planet itself, which has been dry and cold for billions of years and will not bend easily to our wishes. Space exploration has always been more intricate than the posters and headlines suggest. Beneath every photograph of a rover's wheel print lies a web of constraints, failures, calculations, and quiet revisions. Understanding that complexity does not dim the wonder. It deepens it, like looking into a night sky and knowing that every point of light is not just a star, but a story of physics, time, and chance. So as you drift towards sleep, you are allowed to keep the dream. A soft-lit habitat carved into basalt, a window looking out onto a red horizon, a human voice echoing gently through a tunnel, calling others to dinner beneath a foreign sky. But let it be an honest dream, one that makes room for difficulty, uncertainty, and the possibility that Mars, if we ever truly settle it, will demand more from us than we yet know how to give. Thank you for travelling through this thought experiment tonight, and for letting your imagination walk the corridors of a world we have not yet touched. If you'd like to help this journey continue, you can gently tap like, leave a comment, and subscribe. If you feel awake enough, share where you're listening from in the comments, a city, a country, or just under a blanket somewhere. For those who want to support the channel a little more, there is a YouTube membership option as well. It's completely optional, but deeply appreciated. For now, let the questions rest. Mars will still be there in the morning.